So a little more on the notation and definitions here. If the function is called little f there, then we may write y equals f of x. So that's how we say it, y equals f of x, which says y is the image of x under the function f. In other words, the value of the function at f. It's the output when x is the input. So when we talk about it like this, so when we're saying y equals f of x, we're saying that x is the independent variable and y is the dependent variable. So this makes a lot of sense because, think about it, you're choosing what x goes in independently, right? Once you've chosen what x is, the function gives you a certain y. So that y is determined by your choice of x, or in other words, that y is dependent on what x is. Now, if you were to do a function the other way around, if you did a function f is, say, we call it g of y, g being a new function, that would switch. That would switch. In this case, y would become the independent variable and x would become the dependent variable. So it's all how it's defined. Now, most of the time, yes, we do something like y equals f of x, and we have x usually as the independent and y as the dependent, but it doesn't have to be. So a little more on the notation here. To describe where the function is mapped from and to, we often write it like this. All right, and the way we would say this is f takes the set capital X into the set capital Y. All right, so that's how we would read it. F takes X into Y. So this would describe, the picture that we've been looking at, where capital X is your domain, and then we have another set here. Now, this capital Y is this other big set. Within that set, because we're being taken into it, is the range. Okay, so Y can have values that aren't actually in the range. So all the X's are getting mapped, but they're only ending up in the specific part of Y that's the range. So Y itself isn't the range. If you'd like to know what Y is called, Y is often called the codomain. So it has the range inside of it, but it has members that don't get mapped to from X. Okay, so one thing we like to do with a function is evaluate it. So let's talk about some function evaluation. So if we want to find f of 2 when the function f of x is x squared minus 1, we're just think about this function, f of x equals x squared minus 1. It tells us what to do to any x that's put in. It says square that x and then subtract 1. So if they're telling me do f of 2, then I'm really doing 2 in replacement of x everywhere. So 2 squared minus 1, 4 minus 1, I get 3. So f of 2 gives 3. If I wanted to do f of negative 3, I take negative 3, I square it, subtract 1. 9 minus 1, or 8. Okay? Now that's not too hard to imagine, just plugging in numbers. But often we want to plug in things that aren't numbers. So if I want to plug in a, f of a, well, I'm just looking back at the original definition, the rule of the function here, and it says take whatever is given, square it, and subtract 1. So a squared minus 1. That's it. Okay. Let's say I wanted to put in x plus 1. All right, so you can't fixate on what x is. So in the original definition, f of x is x squared minus 1. X is just representative of the input, just taking the place of the input there. So now when I'm doing f of x plus 1, x plus 1 is the whole input. So it is what x was in the original function. So I'm really going to replace x in the function with x plus 1. So x plus 1 all squared minus 1. All right, so remember that the function is defined as just a rule telling you what is done with the input. And the input can be anything. So we have to be flexible. For example, let's say we wanted to do, we're given the function f of x is 2x plus 3, and I want to find f of x plus h minus f of x over h. Now this is an interesting quantity, which we would talk about a lot in calculus. But for this, we're just talking function evaluations. All right, so this f of x plus h, what is that? Well, let's rewrite that over here, and I'm going to use some brackets to make it clear what part is what. So this is x plus h being put in for x. So that means the function says I do 2 times the input plus 3. So I would do 2 times x plus h plus 3. So that's the entire f of x plus h. Then I subtract f of x itself. But f of x just looks like what it is in the original, so it's just 2x plus 3, and I want all of that over h. Okay, so this part was there. Now I just do some simplification. 2x plus 2h plus 3, distribute the minus 2x minus 3 all over h. Notice now the 2x's cancel out and the 3's cancel out. I get 2h over h, or just 2. So this quantity here for this function just simplified to 2. Okay, so that quantity is actually known as the difference quotient when you start talking about it in calculus. And here we're just using it to show you that we don't always just put x in. We don't always just put a number in. We can put anything we really want into the function, even if it's something like x plus h. We can put that in. Okay, let's take a deeper look at domain. So again, we said domain was all the set of inputs. So another way we can think of it is all allowable values to be put into the function. So when we're given some function, we can determine the domain by checking to see what would be allowed in. So why might a point not be allowed in? Well, we've seen plenty of things where things we're not allowed to have. We're not allowed to have zeros in the denominator. So any input that would give us a 0 in the denominator is not allowed. And if we want to stay in the real numbers, we can't have negatives in a square root. So any input that would give negatives in a square root wouldn't be allowed. We'll see in future functions that we'll learn there are other things that won't be allowed, but that's mostly what we're looking at right now. So if I want to determine the domain here for this first one, I'd be looking here, and I see I have a denominator of x minus 3. That means I need x to not be 3. So there are a few ways I could say this. So one way I could say it is our domain is all real numbers except x equals 3, because all the rest of the real numbers are going to be perfectly fine when plugged in there. Or if we wanted to do it using interval notation, it would be -3 to 3 union 3 to infinity, which would just be the whole real numbers, all the real numbers skipping 3. All right, let's look at this one. Well, this is just a nice polynomial here, x squared minus 3x plus 1. There's nothing we can put in that would cause any sort of problem. So our domain is all the real numbers, or if we did in intervals, negative infinity to infinity. So there's nothing limited from the domain of the real numbers. I should note that basically for these, unless otherwise stated, we're considering the biggest possible domain to be all the real numbers.